this is the property of a mutually exclusive event, and this is the property of exhaustive event. So the combined mutually exclusive and exhaustive events would be such that E1 union E2 union E3 and so on up to En would be equal to S, and the intersection of any of two events would always be equal to phi. For example, if we consider a single throw of a die, then if we say that A is the event of getting an even number and B is an event of getting an odd number, then A would be equal to 2, 4, 6 as these are even numbers, and B would be equal to 1, 3, 5 and these are odd numbers. Now A intersection B would be phi, and A union B would be equal to 1, 2, 3, 4, 5, 6, and this is equal to the sample space S. This is the set of all the possible outcomes. So we see that it satisfies this condition and it satisfies this condition. So A and B are mutually exclusive and exhaustive events. So let's consider an example. Two dice are thrown and the sum of the numbers which come up on the dice are noted. Let us consider the following events. A is the sum is even, B is sum is a multiple of 3, C is sum is less than 4, and D is sum is greater than 11. So which pair of these are mutually exclusive? So in this problem we have been given that two dice are thrown and the sum of the numbers which come up are noted. Then we have to consider the following events. A is the event that is the sum is even, B is the event that sum is a multiple of 3, C is the event that the sum is less than 4, and D is the event that the sum is greater than 11. Now we have to check which pairs are mutually exclusive events. Now we see that there are 6 cross 6, that is equal to 36 elements in the sample space. So there are in all 36 elements in sample space, because for the first dice there are 6 possible ways, and for the second dice there are again 6 possible ways. So in all there would be 6 cross 6, which is equal to 36 elements in the sample space. Now we see that A is the event that the sum is even. So it means that we have to consider those ordered pairs x comma y in which x plus y is even. So A would be equal to 1 comma 1, 2 comma 2, 1 comma 3, 1 comma 5, 2 comma 4, 2 comma 6, 3 comma 1, 3 comma 3, 3 comma 5, 4 comma 2, 4 comma 4, 4 comma 6, 5 comma 1, 5 comma 3, 5 comma 5, 6 comma 2, 6 comma 4 and 6 comma 6. So these are the sample points that belong to the set A, which is the sum should be even. Now B is the sum should be a multiple of 3. Now we see that the sum of these two numbers should be a multiple of 3. Now the multiples of 3 could be 3, 6, 9 and 12. The maximum could be 12. So the sample points for set B would be 1 comma 2, 2 comma 1, 1 comma 5, 5 comma 1, 3 comma 3, 2 comma 4, 4 comma 2, 3 comma 6, 6 comma 3, 4 comma 5, 5 comma 4 and 6 comma 6. Now C is the event that the sum is less than 4. For a sum less than 4, the sum could be 2 and 3. Therefore the sample points are 1 comma 1, 2 comma 1 and 1 comma 2 for the set C. And for the set D, we see that the sum should be greater than 11. Now the only number that is greater than 11 is 12. So the sum has to be equal to 12, and that is only possible for a case which is 6 comma 6. That is 6 appears on the first dice and 6 again appears on the second dice. So we see that these are the sample points for set A, set B, set C and set D. Now we find that A intersection B would be 1 comma 5, 2 comma 4, 3 comma 3, 4 comma 2, 5 comma 1 and 6 comma 6. And so we see that these are not mutually exclusive events. This is because if A and B were to be mutually exclusive events, then A intersection B should be equal to phi. Now similarly, if we see A intersection C, then this would again be not equal to phi. A intersection D would not be equal to phi. B intersection C would not be equal to phi. B intersection D would not be equal to phi. But C intersection D is equal to phi. Thus we can say that C and D are mutually exclusive events. These are mutually exclusive events, but these are not exhaustive events. So we can say that C and D are just mutually exclusive events because C intersection D is equal to phi. Till now we have seen different types of events. Now let's come to the main part of this lecture, which is calculating the probability of an event. Now we see that probability is the way of quantifying certainty of an event to happen or not to happen. But now let's see how we actually calculate probability of an event. Probability of an event is denoted by P of A and is defined as P of A equal to number of cases favorable to A divided by the number of possible outcomes. So we can say that the probability of event A happening is equal to the number of cases which are favorable to A divided by the total number of possible outcomes. Now, if an event A can happen in m number of ways and it fails, that is, it does not happen in n number of ways, and each of these m plus n ways is equally likely to occur, then the probability of happening of the event A, also called as the success of A, is given by P of A equal to m divided by m plus n. So if we say that there are m number of ways in which A can happen and there are n number of ways in which A cannot happen, then the probability of happening of A is equal to m divided by m plus n. Similarly, the probability of non-occurrence of A, also called as a failure of A, is given by P of A complement, which is equal to n divided by m plus n. Here we are trying to calculate the probability of non-occurrence of A. So the number of ways which are favorable to the non-occurrence of A is equal to n, because we have seen that there are n number of ways in which A cannot happen. So n divided by m plus n, which are the total number of ways, would be equal to P of A complement, that is the probability of non-occurrence of A, that would be equal to n divided by m plus n. Now if the probability of happening of certain event is denoted by P and that of not happening